Hi, I'm Emin. I recently completed my dissertation and gave a talk on my dissertation to my committee. I wanted to take the time and share my work with everyone by recording the extended version of my talk. I did a systems engineering PhD at UC Berkeley on urban air mobility infrastructure and operations. Urban air mobility, aka UAM, is a complex system of systems. In this vision, passengers leave their origin and go to an origin vertiport using a vehicle or by walk. And then from origin vertiport to destination vertiport, they fly via eVTOLs. And then from destination vertiport, they use a vehicle or by walk, go to their destination. However, in this system, we have sub-complex systems such as vertiports or aircraft fleet. And additionally, we have temporal couplings between these systems. For example, flight times in the system can be from 15 minutes to 20 minutes. Passenger processing times or passenger waiting times can be 5 to 15 minutes, and charging times can be 10 to 15 minutes. So the bottleneck in the system can be any of these three, and this bottleneck will cascade to the other operations. Additionally, we have resource coupling. For example, if you don't have enough infrastructure capacity, then either your aircraft will delay at the origin vertiport or they will hold in the air at the destination vertiport and they will burn energy. And these energy consumption will cascade into your operations. For example, if you burn a lot of energy, then you need to charge more. If you charge more, then your aircraft will be unavailable for the incoming demand. So because of that, you will either lose some passengers, you will have to spill or reject some passengers, or your passenger waiting times will increase. Additionally, weather will have significant impacts in these vehicles. Weather, or especially wind, will increase or decrease your energy consumption or increase or decrease your flight times. Additionally, we can have uncertainty in the passenger arrival process. The demand uncertainty creates cascading effects throughout the UAM system. When demand spikes unexpectedly, we might face insufficient aircraft availability, and that will lead to longer passenger wait times or passenger spill. We take systems engineering approach to UAM. First of all, we will look into infrastructure. We will do vertiport design and analysis, and then we'll move on to the modeling part. We'll introduce you VertiSim, which is a UAM network simulation tool. And then we'll go into the planning. We will optimize network operations while accounting environmental impacts and their particularly wind effects. Finally, we tackle the challenge of real-time fleet control through reinforcement learning approaches to fleet management. All right, let's start with infrastructure. All right, what is a vertiport? Vertiport is an infrastructure for eVTOLs to land, take off, taxi, charge, board, and deboard passengers. We can model vertiports using graphs. For example, TLOFs, which are touchdown and liftoff areas where aircraft take off and land, can be modeled using nodes. And parking paths can also be modeled as nodes. And taxiways can be modeled as links that connect these nodes together. We see a satellite layout here, and this is one of the example drawings of satellite layout. So right now, industry projections suggest thousands of daily flights in metropolitan areas. And we're asking that, can we really do that? All right, what is a capacity and why it matters? We define capacity as the maximum steady-state throughput of aircraft per hour, given that the maximum queuing delay for holding aircraft remains below a specified threshold with high probability. So we define maximum queuing delay because we don't want aircraft to hold like 30 minutes, 45 minutes, an hour in the air because it burns a lot of energy. So we want aircraft to hold at most some specific threshold with high probability. And that's how we define the capacity. And the capacity will impact our network connectivity because if you don't have the capacity, you basically cannot fly that route. Secondly, it will create low capacity will create some network effects, will impact your operations at the other vertiports. low capacity definitely will reduce your service quality and guarantee, and it will cost money in terms of land. Okay, vertiports are actually highly interactive stochastic systems. There are some literature on vertiports and, of course, airports. We draw some similarities from airport literature. For example, airports are modeled with stochastic queuing models. They use single server queuing models with infinite buffer capacity. What I mean by infinite buffer capacity is that they model runways without any capacity at the sink level. For example, they assume there are infinite level of parking paths or gates because airports are actually huge, so you can actually put aircraft somewhere at least. There are other studies on vertiports. For example, some studies develop deterministic integer programs, and they're mainly upper bounds because there is no uncertainty in the system. And some studies did queuing models using single nodes or multi-nodes with independent queues. So in the later part of this presentation, we'll show that why we should not model them as single nodes or multi-node, but in independent queues. Okay, the value proposition of this chapter is that we derive capacity as a function of structural and operational parameters based on queuing delay tolerance, and we're considering the whole queuing network structure of a vertiport. So let's model a simple vertiport using queuing theoretical approach. We model TLOF using an MM1 queue. M here represents Markovian arrivals. The second M represents the Markovian service time, and 1 is the number of servers. So we have 1 TLOF, and we have Poisson arrivals, and we have exponential service rates at the server. That's why we have MM1Q. At the TLOF, aircraft see mu TLOF service rate. So the reciprocal of it, 1 divided by mu TLOF, is the average service time that aircraft see. So in the service time, we can include landing time, when the aircraft lands, if there's any safety check, etc. We can include everything in this. So in the system, we have Poisson arrivals, and once the aircraft arrive, it gets on the arrival queue. If the TLOF is occupied or the parking pads are full, aircraft has to hold. Right? If the aircraft it's aircraft's turn, the aircraft will use the TLOF and then go to parking pads. At the parking pads, it will see mu charge rate of turnaround time, and we have C number of parking pads. Once aircraft finishes its turnaround, and then it will get on the departure queue, and then to go to TLOF, and then from there aircraft will leave the system. Right, and in this case, the arrival rate has to be equal to departure rate in order to have a steady state system. In the system, we model blocking behavior. What we mean by the blocking behavior is that once an aircraft comes at the arrival queue, they have to hold, or they have to wait for the aircraft that are departing, or if the parking pads are full, they cannot use TLOF. And we model this using blocking before service not occupied blocking mechanism. And this mechanism is not well defined except for very limited and special type of queuing networks without a feedback loop. So we cannot solve this problem analytically in its current form. Alright, to simplify the analysis and eliminate the feedback mechanism, we reconfigure the system into a tandem network. In the simplified model, we adjust the service rates of the MM1 queues by howling them to mirror the service dynamics of the feedback system. And that is necessary due to doubling of takeoffs in the reconfigured model. What we do here is we literally break the feedback loop and create two different takeoffs. So here, aircraft first comes to the arrival queue, goes to a takeoff, and then completes its parking turnaround processes, and then goes to another takeoff. So that's why we have the service rates of the takeoffs and the arrival rates that are coming to these takeoffs. And then we realize that we can further simplify this model because in this system, in this first system, we have 3 state variables. And the second system, we lumped these two queues and then use a mathematical trick to calculate the service rate. The service rate mu c NA lambda represents the cumulative effect of parking pad servicing and takeoff service for departure. And this is a state-dependent service rate because NA is the number of aircraft at the parking pads. Okay, in this system we have 2 states. We have number of aircraft at the arrival queue and the number of aircraft at the parking pads. We draw the state transition rate diagram, like you see here, and then we solve the global balance equations. So we can solve the linear system of equations using pi times q equal to 0. Here pi is the steady-state probability distribution of state transitions. So it will tell you what is the probability transitioning from one state to the another. And q is the transition rate matrix, which is you see here. The arrow shows you each component of the transition rates. In a steady state system, inflows has to be equal to outflows. That's why this pi times q is equal to 0. And additionally, we have a normalization term because pi is a probability distribution and sum has to be equal to 1. The global balance equations are written here. We just simply use the state transition rate diagram and created the equations. And using these global balance equations, we could calculate several performance metrics like LQ, which is the average queue length in the airspace. We calculate variance of the queue length. And then by using Little's law, we calculate WQ, which is average queue waiting time in the airspace or holding time. And we also calculate the variance in the queue waiting time. Okay, one reason is that we are solving this in this manner because we cannot isolate these two queues, takeoff queue and parking pad queue or surface queue. Because due to the blocking of the second queue, the parking queue, the arrivals to the second queue are state dependent. So in that case, we actually violate Jackson network assumption. So we cannot isolate and solve these two queues separately, which is actually very easy to solve. Here in this plots we see here is that arrival rate is on the x-axis. We keep increasing that, and then we show the blocking probability at the second queue. So as we increase the arrival rates, the blocking probability increases significantly. And because of that, there's a high interaction between these two queues. So we have to account for that. All right, we also built a queuing network simulator to use it for further analysis. And then we compared results against two-node queuing network because we can compute two-node queuing network mathematically, right? So we use mu takeoff divided by 2 by 30 aircraft an hour, right? Because we have half the rate now. And we kept mu charge as fixed, which is 6 aircraft an hour. And when we compare this with a queuing network simulation tool, we saw a maximum difference of 5.9 seconds in the queuing times, queuing delays, which is 3%, which is very low. So this tells us that we can use that simulator to study different models. Okay, some results. First of all, the fundamental question we are trying to answer is this: what is the maximum arrival or departure rate, or you could call it throughput, we can handle while ensuring that aircraft don't experience excessive waiting times? So more specifically, we want to guarantee that aircraft waiting times stay below 5 minutes with a 95% confidence. The challenge is that we can't directly calculate the exact distribution of waiting times in our complex queuing network. However, based on previous research and the central limit theorem, we can reasonably approximate the waiting times as following a normal distribution. This gives us a powerful statistical tool to work with. So what we do here, we could calculate WQ, waiting time, and plus z-score times the standard deviation of that waiting time, so that we can get the upper bound of the queuing delay. So we use 1.96, which is equal to 95% confidence in the system, and we'll calculate, we'll do the rest of the analysis based on these numbers. In the results, we find that the maximum capacity of a vertiport can be at most half the takeoff rate, or roughly 20% of the surface capacity, which is the turnaround rate times the number of chargers. We need to note that we use Markovian processes in the system. So we use Poisson arrivals and exponential service times. And we also set our confidence level to 95% that we will never exceed 5 minutes of holding delays. So on the plot, we have average charging times on the x-axis and throughput per aircraft per hour on the y-axis. So we could get to 12 aircraft an hour by just using 4 parking paths at the 5 minutes charging time, and then beyond that, we saw diminishing returns. As you add more parking paths, there's not much increase in the throughput, because of the interactions between TLOF and the parking paths, because TLOF is being used very frequently, so you cannot actually go beyond that capacity. We're actually reaching the TLOF capacity in this case, but we don't see this on the higher charging times because the interaction between TLOF and the parking paths are actually very low. And we will see a more deterministic case study where we could actually utilize the 100% of the TLOF. Okay, so we also wanted to understand that how good is our mathematical model compared to the real model, the feedback model, because we use two-node queuing network to approximate the feedback model. So we use a simulation of the discrete event network simulation tool to model the feedback system, and use our mathematical model to calculate the throughput numbers. And the maximum deviation was only 10%. So you don't actually have to build the simulation tool to model the system. You can just use the equations to calculate these numbers. Okay. We also want to show you the confidence level in the 5 minutes maximum queuing delay as the arrival rates increase. So let's pick an example parking path number. Let's pick 10. At around 10 arrival per hour, we are almost 100% sure that the queuing delay won't be more than 5 minutes. But beyond this threshold, further increases in the arrival rate do not substantially enhance the system throughput, but rather they diminish the system's controllability, because it goes beyond this point and it will become very hard to control the system. Okay, so exponential distribution has nice mathematical properties like memoryless property that allows us to do queuing math. However, it comes with a high variation cost. What do I mean by that is that the standard deviation of an exponential distribution is equal to its mean value. We model takeoff service times and charging times with exponential distribution. However, in reality, if you look at airports, you don't see that much of variance in runway service times. Or if you go to a Tesla supercharger, most of the people charge their car for 15 to 20 minutes. So you don't see 2 to 3 minutes or 50 minutes charging very often. And I argue that the charging time distribution will be Gaussian with low standard deviation at these superchargers. So what we did is we said we'll have 60 operations an hour deterministically at each vertiport. That will be the service rate. And then we change the the charge times into a normal distribution. We use mu charge as the average charge time, and the standard deviation is just 20% of the charge time. Okay, we see the big impact of the high variance. Um, the exponential distributed tail of service times, in terms of times case, could actually get at most 15 aircraft throughput per hour, but with the deterministic case, we could get up to 30, the full tail of utilization. However, even in that case, we had to have at least twice the throughput capacity, on the ground. So if you have around like 60 aircraft an hour service rate at the ground, on the ground, then you could actually reach that throughput capacity or full tail-off capacity. We also did unit throughput analysis because we could compute throughput of different configurations, and we can also calculate vertiport footprint areas using FAA standards. We see that beyond 8 parking pads, config 1 starts to decrease, and until 8 parking pads is the best configuration to use. And if you need more, if you have larger areas and need more parking pads, then it's better to go with config 3, which is called pier layout. Okay, in the next section, we'll present you VertiSim Urban Air Mobility Network Simulator. All right, remember this slide? And this is exactly why we built any simulation tool, because none of the off-the-shelf simulation tools could provide us the fidelity we need and the customizability we need to model the UAM operations. I won't be able to play the video for this slide because I'm in recording mode, but I will explain VertiSim in words. VertiSim is a discrete event, single-threaded, asynchronous sandbox for UAM scenario experimentation and fleet management policy optimization. It computes several metrics like resource utilization, vertiport throughput, energy consumption, revenue flights, repositioning of flights, flight occupancy, and passenger waiting time statistics. The software architecture of VertiSim is very simple and extendable. First, you need to provide some vertiport layouts as an input. In the vertiport layouts, you need to provide number of tail-offs, number of parking pads, and their locations, and also the taxiways that are connect these nodes. Then you need to provide some airspace specs. In the airspace specs, you need to provide waypoint locations in the airspace. There are 3D locations, or you can just use a default airspace creation tool of VertiSim, which just creates straight lines between vertiports. You also need to provide airspace specs, which are aircraft dynamics, and seat capacity, the weight, etc. You also need to provide vertiport and network specs. You need to provide the vertiport locations and the number of chargers at the vertiports, the chargers' maximum charge rates and their efficiencies, and the connectivity of the network. You can also provide wind and weather data, where VertiSim will use that to compute energy consumption of the aircraft. You can also provide aircraft and passenger arrival schedule. For a network simulation, you don't have to provide aircraft schedule. You can interact with VertiSim in 3 different modes. One, you can use on-demand scheduling. VertiSim can use its heuristics for dispatch and charging to calculate flight schedules and charging schedules. Second, you can use VertiSim to train your reinforcement learning algorithms and create control policies. Or you can build your own offline optimization tool and create a dispatch and charging policy and put it into VertiSim, and it will simulate for you and then produce more metrics. All right, lastly, I want to talk about the vertiport operations. As you see on the first part, aircraft arrive at an arrival queue, and there they have to halt until they reserve a parking pad and tail off. Once they get the parking pad and tail off, they move to final approach fix, then they go land at the tail off, and then taxi in and do the turnaround process, then taxi out, and then final takeoff and go to departure fix. Okay, the next section we'll talk about a simulation optimization framework for developing wind resilient UAM fleet management. When we talk about UAM, we are envisioning a future where urban skies are bustling with eVTOL aircraft in a clean and sunny day with no wind. This is the ideal scenario. However, the reality is different. We live in a world where wind disrupts our plans, and it can cause flight disruptions, safety issues like separation, turbulence, and passenger discomfort. And that can also increase energy consumption, which then it will lead more capital investments in terms of land and aircraft. So in this work, we look at the wind impact from one aspect, which is the fleet management and sizing. Okay, our hypothesis is this. The variability of wind conditions introduces significant uncertainties into UAM operations, which can affect everything from scheduling and charging to fleet sizing. And our goal is to integrate this wind variability into UAM operations and improve our CAPEX calculation. Okay, there has been several studies that studied wind and its impact on operations. First of all, Schweigenegger and their team studied the impact of wind-induced separation thresholds on UAM network downtime and passenger delays. They realized that there are some seasonal and some timely performance decrease of vertiports. And Pradeep et al. Studied head, cross, and tailwind impact, and they realized that there's a 52% increase in energy consumption from crosswind to headwind when you have 45-mile-per-hour wind on average. And finally, we also found a study on legacy aviation fuel consumption. Wind can increase 14% of fuel consumption of a legacy aircraft compared to no wind scenario. Okay, here's the framework now. So in this framework, we first produce the input for offline optimization using vertiport network simulator. We feed vertiport location and designs, air routes, demand, wind configuration, and some additional configuration to VertiSim. And then VertiSim provides flight durations and energy consumption for each configuration you run. In our framework, for every hour of the day, the energy consumption and flight duration from vertiport A to vertiport B might be different due to wind. So the optimizer takes time-varying charging times and time-varying flight durations and demand as input and produces fleet size, infrastructure size, dispatch policy, and charging policy for the given configuration. We then simulate the optimizer output in VertiSim to get more granular performance metrics. Okay. We explored the impact of wind on operation metrics across a two-vertiport network. The choice of this network is driven by its simplicity, which allows for a focused analysis free from the complexities of larger networks. The area of study spans 150 miles from Monterey to Sacramento, which employs hypothetical vertiport distances ranging from 20 to 150 miles in 10-mile increments. The heading angle from vertiport A to vertiport B is calculated to be 13 degrees relative to north. Okay. We use the rapid refresh data, hourly weather forecast data, with an 8-mile spatial resolution. And utilizing this data set, we extracted 5 years of historical wind data from 2015 to 2019 at 1,500 feet above ground level. We chose the closest grid points along the vertiport routes to capture the relevant wind data. The wind data shows an average speed of 25.5 miles per hour with a predominant direction of 226 degrees relative to the north. The standard deviation is 15.5 miles per hour and 98 degrees, respectively. And that actually reflects significant fluctuations over time. Okay, so we calculated the energy consumption for each hour, for each route over a 5-year wind data set via VertiSim. And we calculated total energy consumption using this equation. Of course, the simulation has much more complex dynamics in it, but what we do is we just sum the energy consumption between these 2 points. So what happens is at each waypoint, the wind speed and direction changes. So between from this point to this point, from point 1 to point 2, the wind speed and direction is constant, and then at this point it is changing. And when we do this calculation, we have 5 times 365 times 24 data points, right? Because we use 5 years of data for every hour. And this is computationally too expensive for our optimizer. And we find a better way of actually preserving this spatial temporal resolution of wind in the energy consumption and flight durations. Okay, another thing is we have very large variation in terms of energy consumption and flight durations. And we wanted to account for that. Variability is important to us because temporal and spatial instability is both realistic and more difficult to optimize against. And the current literature uses fixed median values for wind speed and direction, and that neglects the variability of wind speed and direction over time and space. All right, since we could not use this 5 years of wind data into the optimizer, we process the wind data for optimizer input using VertiSim. We used k-means clustering to capture the wind variation along each route within 8 clusters for each hour. And with some probability, every single day's of energy consumption, or every single hour's energy consumption goes into one of these clusters. So we fed 5 years of daily wind speed and wind direction data into our simulator and calculated the energy consumption and flight duration for every hour for each flight direction. As aircraft move between different wind zones, our simulations adjust to changes in wind speed and direction to preserve wind's spatial and temporal variability in our calculations. So once we obtained this data set, we aimed for an explained variation of at least 70% and identified 8 optimal clusters for each flight direction. So each cluster centroid represents a set of 24-hour energy consumption and flight duration data that reflects varying wind conditions throughout the day. So this figure shows these energy consumption clusters for an 80-mile network. The energy consumption varies from 27 kilowatt hour to 80 kilowatt hour, and flight duration ranges from 25 minutes to 43 minutes. Okay, I'm not going to spend too much time on the optimization model. You can read it on the paper. But what we are trying to do is mainly we're trying to minimize the fleet size. our aircraft can be in idling, charging, and flying state. So we are trying to minimize the sum of number of idling aircraft, number of charging aircraft, and number of flying aircraft. The main dynamics at the vertiport occurs like this. So NIKT is the number of idle aircraft at time t. So we calculate this number by using the following dynamic equation. We sum the previous idling aircraft plus the arriving aircraft at time t prime minus the departing flights at time t plus the aircraft that are finished charging and becomes idle, and minus number of aircraft that begin charging at time t. And here we always use time varying flight times and time varying energy consumption between the flight routes. Okay, we use a demand model and a better model. The details are in the paper, but we use a asymmetric demand from vertiport A to vertiport B, and we use 500 passengers at each direction. So in total, we have 1,000 passengers a day, and we use a charging model that underscores the inherently nonlinear characteristics of the charging process, where charging speed decreases as the battery approaches full capacity. Okay. In the next section, we have the aircraft model and the flight profile. You can read the details of aircraft model. We took the main parts of the model from Sripad and Vishwanathan, and we also use their flight profile. We have 1 mile of separation between airspace waypoints. Basically, so VertiSim employs true airspeed for power calculations and ground speed to determine the flight time. So energy consumption is a combination of both, since it is the integral of power over time. In the existence of wind, the horizontal true airspeed is adjusted to satisfy required time of arrival imposed by fixed vertical airspeed in all phases except cruise, which means that we keep the ground speed same by adjusting the power output to counteract the effects of wind, so that the aircraft can be at the right altitude and longitude and altitude triple at the same time. Whereas in cruise, the airspeed is fixed to minimum power, and just the heading is just adjusted to ensure the aircraft flies towards its destination vertiport. Thus, the power consumption is the same. However, the aircraft will fly slower or faster with respect to the ground, depending on the angle of the crosswind. This means that the energy consumption will still change. The relationship between the required heading, airspeed, and wind velocity is captured by the equations given here. And by solving these equations analytically, we calculate the aircraft heading, and this allows us to define the aircraft's true velocity vector. Okay. Results. So based on our previous work, we use 160 kilowatt hour battery, and we keep 20% of this capacity as a reserve. On the figure, we see energy consumption for each network and for each energy cluster. We observe that the energy consumption can increase by up to 43% on certain routes due to headwinds. This leads to more frequent and longer charging sessions, which in turn can result in aircraft and infrastructure unavailability. So consequently, this may cause schedule disruptions and longer passenger waiting times. Additionally, we observed that this aircraft can make a round trip of up to 80 miles with single charge if it starts the mission with 100% SOC. We'll see the impacts of these on the next slide. Okay, next, we look at the average total charging times for each network. We observe that for the shorter distances, aircraft charges less, which is very intuitive because it doesn't have to burn a lot of energy. And for middle distance flights from 50 miles to 100 miles, aircraft charge after each round trip. And for longer distances, aircraft has to charge after each flight. And for these middle segment, we will observe that there's more load on the grid at one vertiport. So we have to, in this case, when you're doing, considering your operations, you have to actually look at the load you're putting on the grid. Okay. Lastly, I want to share um, the the fleet sizes that we found for each energy cluster. So on the x-axis we have energy clusters, on y-axis we have distance, and here we see the fleet sizes required. So how you can use this information is the following. You can calculate the fleet size, the expected fleet size to serve for a specific demand pattern uh, by counting the wind impact. So what you can do is you can multiply the cluster frequency with the fleet size that we found, and if you sum this, you will get an expected fleet size. Okay, and we saw actually significant impact of wind on fleet size, because for short flights we see fleet size variation of at most 2. We see for medium distances we see 3, and for long distances we see fleet size variation of 6. And that actually results in like 33% of difference in fleet size within energy consumption clusters. Right, we're now on the final chapter. The final chapter is called Online Fleet Management Under Uncertainty, a deep reinforcement learning approach. So we're going to do control, and we're going to do real-time fleet management for UAM use case. UAM fleet management has 3 aspects. One is the dispatch. We need to determine when and which aircraft to serve the passengers. And then we need to determine the route, the destination vertiport of each aircraft that are selected to serve the passengers. We also want to select some aircrafts to do repositioning flights where aircraft supply is not enough to cover the incoming demand. And finally, we need to determine the charging schedule of eVTOLs. We need to determine which aircraft to charge for how long. There are a few challenges in UAM fleet management. The first one is the infrastructure constraint. We have limited parking paths and limited chargers, and the aircraft needs to share these limited resources. The second one is the demand uncertainty. The demand is spatially and temporally asymmetric in the system. And we have limited demand prediction as these systems will operate on demand. Third, network topology. UAM operators will operate in different cities, and at each city they might be using different topology, like hub and spoke or point to point. And the operations strategy will be different for each market. And finally, battery management. These aircraft has limited battery capacity, and battery charging, as we showed before, has nonlinear characteristics. And that's why we try to do real-time decision making, considering dispatch, routing, and charging at the same time. All right, in order to formulate this problem, we first need to define some components in the system. First, we define network components. We define vertiports with number of parking paths, number of teal-offs, and number of chargers. For aircraft, we consider passenger capacity, battery capacity, and associated reserve. We then introduce service time windows and the allocation rules. Our decision-making interval is 5 minutes, and within these 5 minutes, we have continuous passenger arrivals. And we observe waiting time bins. So we observe how many passengers are waited between 0 to 5 minutes and 5 to 10 minutes. And after 10 minutes, we consider that these passengers are spilled, or they leave the system after 10 minutes of waiting time. And passenger allocation is done based on first come, first serve. And we consider aircraft capacity and the number of existing passengers at that time for that origin destination pair. And our objective is to maximize passengers served and minimize operational costs. We use Markov decision process formulation to formulate the problem. First, in our state space, we have vertiport states, aircraft states, and the system time. In vertiport states, we have waiting time bins. We observe how many passengers are each waiting time for each OD pair IJ. And we also observe number of spilled passengers for OD pair IJ at time step T. For aircraft state, we have status, state of charge, location of the aircraft. Status can be fly, charge, and idle. In this here, we have an environment that we described before, which is VertiSim. In VertiSim, we have much more detailed status of aircraft. In the flight phases, we have hover climb, climb transition, climb, cruise, descent, descent transition, hover descent. But for reinforcement learning agent perspective, we only need to know that aircraft is flying for decision making. That's why we simplified the state space in this case. State of charge can be from 0 to 1, we discretize that. And then location can identify two things. One, if the aircraft is flying, it describes the OD pair index. If the aircraft is on the ground, it is the vertiport index. The action space consists of a set of actions for each aircraft. Aircrafts can take several actions. Fly from I to J, charge, and do nothing. The size of the action space depends on the number of vertiports we have. Each charge action takes 5 minutes. After 5 minutes, aircraft becomes idle again, and the RL agent can take charge action to charge it more. And we have a very large state space and action space for this problem, but we apply action masking to significantly minimize the available actions and explorable state space so that we could solve this problem. Our reward function consists of 3 parts: revenue minus expenses minus spill penalty. We use spill penalty in order to accelerate the learning. The revenue is calculated as follows. We multiply number of passengers that are flying from I to J times the fare of IJ. The fare IJ is determined by the distance times the seat per mile. The seat per mile parameter is $3 per mile for our case. And we calculate number of trips by looking into the aircraft capacity and the number of passengers that wants to fly from I to J at time T. Here, kappa IJ at time T shows us the flights that are at time T that are going to fly from I to J. So we could get the capacity for time T and then determine how many passengers will fly for the time step. And we calculate the number of passengers by just looking at the waiting time bins. The expenses has 2 parts. The first part incurs when we charge the aircraft. We calculate how much energy we added into the aircraft at each charging session. So there's a state of charge. There's a percentage difference times the battery size and times the price, kilowatt hour price for that city. And plus, we add cost available seat mile term. So this is a parameter given for cost available seat mile. So we multiply this with the number of seats we have and the distance of the flight. The next spill penalty is very simple. We multiply number of spilled passengers for OD pair IJ and multiply it with alpha parameter. Finally, we have some constraints. We cannot have less than minimum SOC and maximum than SOC max. And in order to fly to a destination from I to J, we need to have the energy requirement for I to J and plus the reserve. So at the end of each flight, we have to have at least SOC reserve. Okay, we solved this problem using 4 different policies. We developed an integer program, we use RL, We use greedy policy and random policy. Okay, the integer program provides us a theoretical upper bound because it has the complete information of demand and it acts accordingly. So it tries to minimize spill and number of flights, which means that we're trying to maximize the number of passengers serving and minimizing the operational expenses. We have few constraints. You will be familiar with this one from the previous chapter. It defines vertiport dynamics. The next set of constraints defines the domain of spill. Spill has to be greater than or equal to 0, and spill is defined the difference between passenger demand and the supply we provide. We also fix the fleet size in this problem, and we don't allow aircraft to fly when they have less than reserve SOC. And finally, the start state has to be equal to end state so that we can repeat the same policy when we see a similar demand. Okay, the reinforcement learning algorithm consists of an RL agent, of course, and the interaction with an environment, which is our simulator VertiSim. So RL agent provides an action and gets state, reward, and action mask in return. And through thousands of interactions with the environment, it learns the model of the environment. It learns the state transitions, and then it acts accordingly. So I'm not going to lecture you on a very well-known PPO, proximal policy optimization algorithm architecture, but what we added here is we added LSTM layers, which is also not new, in order to capture the temporal difference among our in our problem. So we also, as I explained, we use action masking, and action masking is determined by the aircraft current status. So if any aircraft is flying, you cannot assign charge to that aircraft. And it's also SOC also determines the action masking if we don't have enough battery, enough charge to fly to certain destinations. We just mask out those destinations. Okay. Greedy policy, basically like rule-based policy. We have policies for charging and dispatch. For charging, it's very simple. If the SOC of any aircraft is below 20%, we charge it to 60%. For dispatch policy, we look at the aircraft occupancy at that time. If we could satisfy the passenger occupancy, we create a flight. So for a small aircraft, Joby S4 aircraft, if there are 4 passengers accumulated to fly to the same origin destination pair, then we create a flight. Next, we look at the maximum waiting time threshold. If any passenger is about to exceed 10 minutes threshold, waiting time threshold, if there's any available aircraft that can fly to that route, we create a flight, and we get the rest of the passengers with them. And finally, we do repositioning based on supply and demand. Repositioning logic is complex in the sense, but you can read in our paper, which is going to be submitted very soon, to learn about the repositioning logic here. Okay, the random policy provides us the lower bound in terms of reward. And random policy just randomly picks action for each aircraft among valid action. It uses uniform random distribution to pick actions. Alright, the experimental setup and result. For the results, we establish 2 scenarios. One for the validation of the RL policy, and the other one for the multi-vertiport airport case study. For validation, we choose a small problem that integer program can solve. We use a 2 vertiport network with 1,000 daily passengers and 5 aircraft. We assumed large vertiports to eliminate airborne holding, as integer program does not consider vertiport capacity. This simplified scenario allows direct comparison with the optimal solution, which becomes computationally intractable for larger networks. We then consider a star network configuration where a central hub vertiport connects directly to multiple spoke network vertiports. Star networks are actually particularly well suited for initial UAM operations as they concentrate resources at a central hub while providing direct access to multiple destinations. The hub is located at a major commercial airport, LAX, and the spokes are located in various business centers and cities in the broader metropolitan area. We assume that the demand for UAM is mainly driven by airport accessing egress trips of passengers on legacy flights. The passengers' demand for UAM is obtained from the demand model proposed in the first citation here in the slide, and the spatial distribution of demand across various spokes is obtained from the second citation. For both scenarios, we generate 200 days of passenger arrival data using a single stochastic process defined by our demand generation function. We allocate 150 days for training and reserve 50 days for testing to ensure consistent evaluation of the algorithms. We benchmarked 5 different policies on the validation scenario. We tested random policy, greedy policy, integer program, pure PPO, and the PPO's LSTM variant. The primary performance metric was average cumulative reward. And the solid lines here shows us the average cumulative reward for the benchmark algorithms. The upper and lower bound of the shaded bands shows the maximum and the minimum cumulative reward received by the algorithm. We trained RL algorithms for 2.3 million steps, which means that they took 2.3 million set of actions. The PPO-LSTM variant achieved better performance compared to pure PPO, and we think this demonstrates the value of incorporating temporal dependencies in the decision-making process. The PPO-LSTM converged to a policy that generated average cumulative rewards approximately 12.5% below the IP optimum, while the pure PPO's performance stabilized at around 15% below optimal. And the optimality gap is further increased roughly 2.5% on the test set for both algorithms. And this relatively small gap is particularly noteworthy given that the RL agents operate without perfect information about future demand, unlike the integer program, which has complete future demand knowledge. All right, based on our validation results, we selected PPO plus LSTM as our primary RL algorithm for the larger network evaluation. We evaluated this algorithm's performance on a larger, more realistic network with 1 hub and 8 vertiports. For this expanded network, the integer programming approach became computationally intractable due to the exponential growth in variables and constraints. Therefore, we compared the RL approach against the random and greedy policies. The experiments used test data with an average daily demand of 2,000 passengers that are generated using our demand function. We tested 3 fleet sizes, 25, 30, and 35 aircraft to understand performance under varying resource constraints. The figure here shows the average spill percentage and standard deviations across the test runs for each policy across different fleet sizes. The performance gap between RL and the baseline policies remains substantial as fleet size increases. And in general, the marginal benefit of adding aircraft diminishes as the fleet size increases. To better understand the operational differences between policies, we analyzed the average number of daily flights and average flight occupancy values generated by each policy. The random policy consistently generates the highest number of flights from 824, 1,824 goes up to 2,513 flights a day, but achieves the worst spill performance, which indicates inefficient aircraft utilization through unnecessary positioning flights, charging, and idle decisions. The greedy policy maintains a relatively stable number of flights, which is the lowest number of flights across different fleet sizes, and it demonstrates the limited capability of effectively repositioning the aircraft. The RL policy, on the other hand, shows an interesting pattern in flight counts. Initially, it increases from 1,206 flights a day with 25 aircraft to 1,321 flights a day with 30 aircraft, then slightly decreases to 1,316 flights a day with 35 aircraft. We think this pattern suggests that with more aircraft available, the RL agent requires fewer repositioning flights to maintain service quality as aircraft availability becomes less of a constraint. And finally, I would like to talk about an idealized scenario with unlimited aircraft availability that processes this test set demand. And we found that 932 flights is required to serve whole passengers while adhering to key operation constraints, like passengers were only pooled with others sharing the same origin destination pair, and no passengers waited more than 10 minutes for departure. So when we compare RL policy's higher flight counts compared to this theoretical minimum, it reflects the necessary reposition flights to maintain service quality across the network with limited aircraft supply. So this additional flight overhead was about on average it was 37%. Okay, so this figure shows the average cumulative reward across different fleet sizes. And due to the high spill penalty, which was minus 100 per passenger, policies with high spill rates incur substantial negative rewards. The RL policy achieved progressively better performance as fleet size increases. It moves from minus 1,217 to 10,051 for 35 aircraft. Um, and our choice of a high spill penalty is actually deliberate, and it deliberately emphasizes passenger service quality over operational cost efficiency. A lower penalty would likely yield different reward patterns and potentially positive rewards for more conservative operating strategies like greedy policy. We then evaluated system scalability by testing three demand levels using 2,000, 4,000, 6,000 data passengers. And while we, in this case, we fixed the fleet size to 35. And these analyses, revealed some fundamental differences in how each policy handles growing demand under resource constraints. The RL policy's economic performance improved significantly with increased demand, with rewards growing from 10,051 to roughly to $74,000, and despite higher supply rates, of course, because of higher demand. And this improvements we think stems from two factors: high passenger volumes generates more revenue, of course, and better capacity utilization, as shown by these increased occupancy rates shown in these parentheses. And in contrast, the greedy policy's performance deteriorates under higher demand. Um, while it achieves reasonable spill rates at 2,000 passengers, like 12%, and if performance degrades sharply at 6,000 passengers a day, it goes to 25% spill. And this actually exposes a key weakness. Reactive decision making for this type of on-demand system becomes increasingly inadequate as demand grows, even though occupancy rates improve. All right, now we're at the conclusion and future research directions. First, we're looking at the infrastructure and capacity, and we saw that we could only achieve roughly 50% of theoretical maximum throughput under strict delay constraints. And this tells us that we need larger vertiports than the industry and academia estimates. Next, we looked into environmental impacts, specifically wind impact. And wind can increase energy consumption by up to 43%, and it might require us to use 33 more aircraft for the same service level compared to no wind scenarios. So we have to be incorporating wind into our planning algorithms. Lastly, for operation strategy, these myopic decision making becomes inadequate as network complexity grows, and it requires us to shift towards adaptive and data-driven approaches. All right, in this last slide, I would like to talk about the future development of VertiSim and research directions. VertiSim has been my baby throughout my PhD, and soon we will open source this tool to serve the community, and we will ask from community to further develop it. VertiSim provides a comprehensive foundation for UAM network simulation, but several key areas present significant opportunities for technical improvement and expanded capabilities. Three critical directions for future development emerge from our research experience. The first one is the heterogeneous fleet support. The current implementation of VertiSim supports only homogeneous fleet operations, and that limits our ability to study complex interaction that would arise in real-world OEM operations with multiple operators. The second one is the advanced battery modeling. The current battery model in VertiSim employs a simplified approach based on electric vehicle charging characteristics. And if your use case allows it or makes it meaningful, you can use physics-based models that account for battery degradation over time with multiple charge cycles. Or you can introduce temperature effects on charging efficiency and battery performance. You can also do detailed charging dynamics, including variable charging rates and thermal management requirements. And the last one is air traffic management integration. I know it's not easy to integrate air traffic into a discrete event system, but there are smart ways of doing it and getting meaningful metrics out of that system. And the one final thing is that our reinforcement learning approach demonstrate promising results for UAM fleet management, but several important limitations and challenges remain to be addressed. The current framework operates under idealized conditions with perfect information about aircraft and passenger states. Real-world implementation will need to contend with imperfect sensing, communication delays, and uncertainties in state estimation. You could introduce those things in the MDP model. And another fundamental challenge lies in the temporal resolution of our MDP framework, and particularly in managing aircraft holding patterns. The current 5-minute decision interval, while computationally efficient, proves inadequate for holding pattern management. Um, and in this system, even brief holds significantly impact operations, right? So this limitation cannot be easily addressed through a simple state augmentation, as the underlying issue stems from mismatch between the decision interval and the operational time scale of holds. So the challenge is compounded by the difficulty in designing appropriate reward signals, right? These, for example, like energy cost during holds are relatively small compared to operational cost, and it makes it harder for agent to learn making optimal holding strategies. And while these shorter decision intervals could theoretically address these issues, they would substantially increase computational complexity. And additionally, alternative approaches like implementing holding penalties or episode truncation risk introducing undesirable learning behaviors. Like severe penalties can destabilize learning, while episode truncation might encourage artificial termination to avoid penalties. And we need to find an effective approach to incorporate holding pattern management while maintaining stable learning and computational tractability, and that remains an open challenge for future research. For the research directions, I would suggest this. As UAM networks scale up, understanding the dynamics of multi-agent system becomes increasingly important. And I think future research should investigate distributed control architectures that can coordinate actions across multiple vehicles and vertiports, while maintaining computational tractability, of course. And this includes exploring multi-agent reinforcement learning approaches that can handle the increased complexity of coordinated decision making across multiple autonomous agents. Additionally, the framework should be extended to incorporate multiple competing operators sharing limited resources. And this would enable investigation of market dynamics and strategic behavior in UAM operations, particularly regarding resource allocation and pricing strategies. And lastly, I would like to talk about environmental and societal impact. Um, this is a very important topic, I think, because the community acceptance won't be very fast for UAM, and because of noise, visual pollution, equity issues. So further research should also address these. Thank you very much for taking the time and listening to my talk. I hope it was useful for you, and if you have any questions, please don't hesitate to reach out to me.